Hello, everyone. Good afternoon. Good afternoon. I think someone said good evening. Does that mean you're in a different time zone? That would be, yeah, I mean, isn't after midday morning time for computing people? I'm not sure. It used to be for me, but not anymore. Okay, hello everyone. Hope you had a good day yesterday following the lecture. We're going to continue today doing all sorts of exciting things, and let's get started. All right, and Thomas is in the chat today, so he will be answering your questions. So please fill the chat with lots and lots of questions. We want to hear what your thoughts are. And any questions that you might have, because we're starting to kind of get into the nitty gritty. We're starting to get quite detailed as well. So we really want to know how you guys are going and whether you have a question about anything that we're covering. So I've taken a note of the string thing. I'm going to do a little sideways video about strings, because I think strings in C in particular are quite fiddly, but quite fun, because you can just play around with that null terminator and shove it wherever you want. So they work slightly differently to other languages as well. So we will do that. But I thought I'd get the lectures out of the way first. And hope everyone is almost finished their assignment. It's due in 8 hours, just under 8 hours. So very exciting. Then you might have a few days to actually, I don't know, relax, because I guess you have all the other things that you have due as well. So somewhat relax by like an 8. Okay, so yesterday we talked about multi-file projects, and we will continue today to divvy things up into multi-files. We talked a little bit more about memory, and we're going to talk a little bit more about memory today. We didn't do a slow intro to linked lists, but we are going to intro the linked list today, which I think will actually work a lot better. And then I really want you to, when I introduce the linked lists, I really want you to be like right there asking lots of questions, because linked lists are pretty important, and they will form really your second assignment. So I really want you to understand them quite well. And yeah, just slowing stuff down as well, so that, oh my God, Neil just freaked me out. Haven't started. Okay, and Sienna said that she gave up in stage 4. That's not a bad thing. You know, stage 4 is not worth a lot. It's really just there as a bit of a challenge, a bit of an exciting thing for you. I don't know. Could be an exciting thing for you if you've got time. So it's not worth a lot. Don't forget that most of the marks are sitting in stages 1 and stages 2, and then a little bit of stage 3. So you can get very good mark just by doing good style and doing the first 2 stages completely, and a bit of stage 3 even, and you've got yourself quite a good mark. All right, today, linked lists. And also I wanted to do a few more things as well, in that I wanted to talk about struct pointers, which was something that someone asked yesterday. We didn't get to it yesterday, so we're going to do it today. Okay, let me go to this to demonstrate something. Okay, so I'm going to demonstrate how to make a pointer to a struct, and then how to access it, how to actually play around with it, because that's going to be important for our linked list application. So let's do, okay, our normal struct. So let's say I've got a normal struct, and it's going to be a struct dog. If you haven't guessed, I'm quite obsessed with dogs. And the struct dog has a char name in it. So it's got an array, so a string, really, a name of the dog. And it's got an int age in it, so an int how old the dog is. Okay, then I'm going to declare my struct. So I'm going to say struct dog, and the variable name is Jax. So I've created a variable Jax, and it is of type struct dog. So that means that Jax inside it has 2 members. It has the name and the age. And I will access those members by using the little dot. So now I want to be able to do a few little things, okay? So first of all, before I do the pointer, let me first go through where we're just accessing the normal member. So if I initialize my struct, so let's say I want to put the name Jax into the name member of that Jax struct, I will use the string copy command because I'm copying across a whole string. And that means I've also included a string.h standard library up here. So I'm going to copy across by using the string copy command into the jax.name member. So I'm going inside my variable name Jax, the struct member is name, and I'm copying the string Jax into it. And then I'm also initializing the age by saying jax.age is equal to 6. And that allows me to then, printf, Jax is an awesome dog who is 6 years old. So if I were to run that, then it will print out for me. So it'll show me that it accessed those members okay, and I initialize them okay as well. Okay, so now let's see what happens if we create a pointer to our struct, okay? So I'm going to create a pointer and it's to a type struct of that dog. So I'm going to want to point, so struct dog pointer is what I'm creating. And that's what I'm saying here. So I'm saying struct dog pointer and I'm going with, I forgot to give it a name. Okay, I'm going to call it Jax pointer, and then I'm going to set it to the address of my Jax variable. So I'm setting it to the address of this lovely thing here. So this pointer points to the variable Jax of type struct dog. So it's pointing to the address of that. Now, if I were to initialize this pointer, so I'm going to comment out my normal access because I'm going to do it via pointers, okay? So if I'm going to initialize the struct by using my pointers, you would think, how do you think I would access my pointer? What do you think? And it is whatever you think would be probably the normal. So if I want to place something, normally I will go jax.name. How do you think I'll do it for the pointer? What do you reckon? So I could dereference the pointer first. Okay, yeah, so that's right. So Sienna's saying star. Okay, Richard and a few other people are ahead of the game. They know the shortcut already. So yeah, so if I dereference it and access Jax pointer, then I can access the member of whatever I want. So let's say member is name, and I can copy Jax into it. Okay, and so this is really a way to access it, right? And it's pretty nice because it allows me to dereference the pointer and then access the right member. But as you can imagine, this can get pretty messy. I need brackets and I need the star all the time that I'm going to be dereferencing, okay? So what it means is it could get quite messy if I'm doing it a lot and if I'm using these struct pointers a lot, okay? So it's not, even though this works, this is really how it happens. In C, we also have a shortcut for it, okay? Because we don't want to have this beautiful mess of brackets and stars everywhere because it's very easy to get lost with open brackets, close brackets, open brackets, close brackets. So in this case, what we do is we have the shortcut, and a few of you already know the shortcut. Instead of using that, star and the pointer and then the dot, what we do is we use this lovely arrow here, okay? And what the arrow does, it dereferences the pointer and it points it to whatever member, so it accesses whatever member is part of it. So me using this arrow is the same thing as me dereferencing that pointer and then, accessing the member of the struct. Now, someone's asked why I'm using string copy, and the reason I am using string copy is because otherwise I cannot copy in the string into my member unless I do it character by character. Okay, so I use string copy as a quick way So I'm borrowing the function string copy, and I'm using it so that I can easily put a string into my member of that struct. So now I've accessed that, and now I want to do the age, and I can do it the same way. So I've got the pointer, and instead of using the dot, if I'm accessing a pointer, I will use this lovely arrow here. And then I will access the age member, and it's going to be equal to 6 again. And so now really what I'm going to do up here is the same thing. So I can do, let's do Jack's pointer. And how about I do one with the stars, just so that you can see that it does a similar thing, but just a more annoying way to do it. Have I got lost in the brackets? No, that looks okay. I mean, it'll tell me if it's not okay. Okay, let's try doing it now. And it's okay. And it's running perfectly anyway. So you can see that it's a lot nicer to just kind of use an arrow than to use this kind of notation. It's a lot faster. So Neil, line 20, if we've got line 24, well, I think Thomas is answering it. I can see him typing. Okay, so I'll let him answer it. So instead of using this, we've got our shorthand. And the reason we have this shorthand in C is because we do it so much, okay? And we do it so much when it comes to linked lists. You will be dreaming of arrows. You will just, that will be your dreams, nightmares. I'm not sure. Sometimes after assignment 2, after running help sessions, I often went to sleep and I couldn't sleep because all I could just the arrows, arrow, arrow, arrow. So just giving you a bit of a heads up, the feels that you will be feeling soon. But it can get quite fun. Okay. So that is just really how to use that shorthand way of accessing a pointer to the struct. Hang on. Yeah, no, Thomas is rewriting. Yeah. So I'm going to need the pointer and this one because this pointer is to this struct and this pointer is of type struct dog, okay? So if I just had the pointer, so if I just had this, what is it pointing to, right? What is I have, it's not pointed to anything in this way. I haven't initialized it. In this way, I only have it there. So if I didn't have that struct dog Jacks, then I wouldn't have anything to point this one to. I want it to be to the address of this pointer. Okay, so that is the lovely struct pointers. So now let me, and it sounds like a few of you have either gone ahead or you are, how many of you have heard of a linked list before? How many of you have heard of it, used it, loved it? Tim, the pointer doesn't necessarily need braces, but I'm forcing a certain order to it, which is why I always like to use braces. Okay, a few people read a little bit ahead. A few people have heard of linked lists. Someone asked, how do we reverse a linked list? Reversing a linked list is quite a difficult question. It is not one I would like to do until towards the end of the term, if at all, because reversing is quite a difficult thing. You've got to really keep track of a lot of moving parts. If you are not just printing it out in reverse order, if you're actually reversing the linked list per se. All right, heard of before? Okay, linked list is a, so code, the usual in week 7. And okay, I'm going to leave it for now. Okay, so a linked list is this lovely structure, okay, that is, it's missing a slide. I'm sorry, I'm missing a slide. Someone's using the word stack in there. We don't do stacks till the end of term, my goodness. So a linked list is this wonderful structure which allows us to really use memory in a really neat way and really efficiently as well. So someone asked yesterday, what happens if we have this unknown number of things that we want to keep adding into some sort of list, okay? And we don't know how many things there are, so we don't know how much memory we would need to get for them. Because an array, you kind of really need to know because the memory bits are consecutive, you need to know how much memory I need to create for it to start with. So if we do not know, if we want to be creating one thing at a time and inserting them in, then that means we want a linked list structure, okay? So that's what happens when we don't know how many things we're going to need, because in a linked list, we're going to create one item at a time as we need them, and we're going to dynamically allocate some memory for that item, and then we're going to put it into our list. So the most important thing, so each item in a linked list is basically called a node, okay? And what that means is, I'll draw it up for you, hang on. Okay, so a linked list has something called a node. And let me just go like this so that you can see. Okay, so let's say we have this lovely struct node, okay? And this is one element of a list. So let's say we have this struct node, and what happens is this is my node, the blue. So this whole thing is a node, and I've made it a struct. So inside that struct, I've got a data. So let's say this is my int data here, the green, and the red one is my struct node next. So that, what does that mean? It means that it's a pointer to the next also of struct node. So it's pointing me to the next element in the list. So this is my next pointer, and this one here is my data. So what a node allows us to do is it allows us to store two or more things in it. But the most important thing that a node has is this pointer to the next node. Because the memory is dynamically allocated for nodes, what happens is every time I call malloc and I create one node at a time, I might have a node here, and I might have a node here, and I might have a node here. And I need to be able to link them, because perhaps I'm going to go like this, and then I'm going to go like this, and then I'm going to go like this. So every time that you have a node, I can rearrange that list just by changing where things are pointing to. So a linked list structure, if I draw it perfectly, okay, but this is not how it looks in memory. Each one has one node. This is my struct node. Inside the node, at a minimum, you might have some data and a pointer to the next thing. So let's say I have a list. I drew those pretty things, and now I'm not using them, and I'm just drawing it straight up. Sorry. I might use the pretty things next. Okay, so what I have is, for example, if I have a list with 1, 2, and 4, okay, I might put 1 in here, and then I want to go to the next item in the list, which is 2. So if this node is 2, then this next pointer is going to point me to the address of this node. And then if this one, oh, it's not, oh, I'm sorry, you cannot see what I'm drawing because I'm drawing it on an iPad, but updating it on the, on here. I'm so sorry, everyone. Fail, I was getting so excited. Now this is, let me erase it and start again, because now no one knows what on earth I was doing. Yeah, no one could see it because I forgot to scroll down. Okay, so a linked list is made up of many nodes, okay? You can have as many nodes as you want. You make the nodes as you need them. So let's say I've got a list of 1, 2, and 4, and I want to create the nodes for it, okay? So each one of them has a node, and I've created a struct for it. And my struct has 2 things in it. It has the data. So if I'm using this struct here, it has my data and it has the node next, which is a pointer to the next node. And it means that you can arrange your nodes in any way that you want to. Because remember, these nodes are not necessarily one following the other, following the other, following the other. The nodes are arranged in such a way that you can take any bit of memory that you have when you take a node, and then you want to point to that bit of memory because they're spread out all over your heap. So what happens is if this is my 1 and this is my pointer to the next element, and let's say my 2 is over here, and let's say this is my 4, okay, then what happens is the 1, I wanted to point to the 4, so my pointer is going to point to this node, and what happens here is that the 2, I wanted to point to the 4, so it's going to point to the node of 4. And where is 4 going to point? What do you reckon? Because there's nothing after 4, so where do you think 4 can point to? Where's 4 going to go? You're going to go, you don't need pointers to pointers. You're pointing to a node. Yes, whoever said null, well done, because there's nothing else left. So I'm going to finish with a null. So what it means is that linked lists, no, they're not creating one extra bit of memory because null is nothing. There is nothing there for null. So what you have is you have node, 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 then there's nothing there. But I also need a way to know where on earth does my list start? Again, because it could be anywhere in that memory heap, I need to know where is this list starting. So in the very beginning, and usually we call the start a head, okay? I'm going to have a pointer to the head, which points me to the first node, okay? And the head of the list is really just a pointer. So it's just my pointer that will point me to the first node of that list so that I know where on earth I need to start, okay? So what happens is you've got a pointer to the first node here, okay? And then that first pointer will point to your first node. And then it points to the next node and to the next node, and then it goes to a null pointer. So let's say we have a list, and I'm going to go to the pretty boxes that I've drawn for a second. Let's say we have a list with numbers 1, 2, and 4. How will this look in a linked list structure? Lisa, excellent question. Are nodes always structs? They are always structs because they always have to have some piece of data because otherwise what am I storing in that node? But also they will always, always, always have this pointer to the next node, okay? So you always want to know what comes next, what comes next, what comes next. So you're always going to have a pointer to the next node and at least one piece of data because that's why you're creating the linked list. And you can have more than one piece of data because your struct can obviously have more things in it than just, one integer. That's just a very simple, use of linked lists. But you can have an array in there, you can have a char in there, you can have a double in there, you can have whatever you want in there. And then each node is going to have all of those same things in it as well. So I've done memory addresses here as well. So let's say I've got a pointer to the head, and this is my pointer to the head. So it's pointing to the address 0xff0, which is the address of my first node, okay? So I'm pointing to my first node, and inside my first node, I have a structure of a node. So I have an int1, and I also have a pointer to the next item in my linked list. So I'm storing 0xA44, for example. These are just random numbers I've made up, okay? And that means that this is my next item because it's sitting at this address. So the node is sitting at the address 0xA44, and that's where I'm pointing to, okay? So the next thing will have, let's say, the 2 in it, and then it has a pointer to the next memory address as well, which is, let's say, 0x3b4. And that means that my next node is sitting at that address. So I'm following where this address is taking me to the next node. It's taking me to this node here, and this node has a 4 in it. And then where am I going from this node? I'm heading towards nowhere in this node. I'm going to null because it's the end of the list, okay? So my next node is actually, there is no more nodes. It's going to be null. There is nothing, it's a null pointer. So someone said, do we get the address of the first node using a struct pointer? Basic question, but just to clarify, it's a great question. And I think Thomas is answering it. I can see him typing, so I'll let him answer it. But yes, you will get the address of the first node using a pointer to a node, because you want to have that lovely, you want to know what you're pointing to. So do we have to initialize the memory address in the nodes, or does that happen automatically? Excellent question. I mean, I wish it happened automatically, because then you wouldn't dream of those arrows as your nightmares. But it does not happen automatically. You have to tell the linked list what to point next to and what to point before it to. So, and we're going to do that next week, where we insert something and change where it's pointing to and where it's going. Today, we're just going to keep it simple. We're going to insert something at the beginning of a linked list. We're going to make that linked list, and we're going to learn how to traverse the linked list as well. I mean, I'm calling it a nightmare, but honestly, with linked lists, you have this nightmare of those arrows and what's going on. And sometimes you can get very confused in what's happening. Arrow, 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 next, where am I? But the one magical thing about linked lists is that they lend themselves so well to diagrams, okay? If you draw a diagram of a linked list, if you just draw a simple diagram like this, your code will become completely obvious, okay? It will almost write itself for you, because you will straight away see where the arrow is meant to point. And I will move you along. I'll show you how to move yourself along the linked list to make it easier for you in a diagram to know what you're doing. So the next 2 weeks, you're really gonna, I'm sorry, see my terrible drawing skills, because I'm going to draw up everything that we do so that you can see. If you draw a diagram of a linked list, you make the whole problem a lot easier. You're really breaking it down to this really simple structure, because a linked list is actually quite a simple data structure. It's a very useful one. And, you know, the difficulty just lies in trying to decide where are you pointing to next, or where are you inserting to, or where are you in that list, what's going on. So this is, at this point in time, is where you're actually going to constantly be accessing null pointers, I would imagine. That's just what happens. Don't be scared of it, but that's why we always tell you, don't dereference a null pointer. It's a big no-no. You're going to see that happen when you play with linked lists, and that's okay, because I think it's a great way to learn, what not to do, and you'll probably still keep doing it as well. Assignment 2 is all about linked lists. Yeah. So those are the 2 data structures that we want you to learn from this course when you go on in computing: arrays and linked lists, which is why the first assignment is all about arrays and the second assignment is all about linked lists, okay? And don't forget, we are always there to help you as well. Forums, help sessions, and so on and so forth in your labs. Ask lots of questions as you become familiar with it. It is really all about the linked list now for the rest of the term. So I hope you like linked lists. Okay, so why do we have this linked list? You're probably thinking, we've done arrays, I'm done with this. Why do I need more data structures? Different problems require you to use different data structures. Sometimes you can solve one problem with, 5 different ways. Often there is a more efficient solution, but again, we don't care about efficiency in this course. But we will be forcing you to solve things using linked lists for the next few weeks, just to give you practice using linked lists. So the reason we do use linked lists is because they're a lot more efficient, because they're dynamically sized. It gives me control over the linked list. I can create a node and I can delete a node, so I can grow and shrink that linked list as I need to. Okay, so that's efficient for memory, because I can make space for a node and then I can get rid of that node and get the space back. So elements of the linked list, which are called nodes, they don't need to be stored in memory one after the other, like in an array. So in an array, each index is directly following the other one. And that's how we're able to access whichever element of the array, because we can calculate where it's sitting based on its index. This is not the case for linked lists, which means that a linked list can only be accessed sequentially. So you have to go through the whole thing to get somewhere, right? You can't just go, oh, I want the third thing from the linked list. So give me the third thing. No, you have to start from the head and you have to get to the third thing first before you can access that third thing. So you can add or remove nodes as needed. You don't have to worry about the size unless, of course, there's no more malloc left. There's no more memory left. So then you do have to worry about the size then. But other than that, you don't. And you can change the order of a linked list easily just by changing where the pointers are pointing to. Again, you can insert things easily by changing where the pointers go to. Yeah, so they will give you a certain amount of freedom that arrays couldn't give you. But they will also intimately acquaint you with pointers. So I actually think that pointers become a lot more obvious when you do linked lists, and they become a lot more clear when you are playing with them in linked lists because you're using them in such a, just such a basic way, like it contextually it makes sense. So I hope that if you are still iffy on pointers, this will be your moment to shine. That will make a little bit more sense to you. And also structs, because each node is really a struct because it's a combination of things that I've made to build up a node. And I cater that struct to what I need it to be based on my problem, except that it always has the pointer to the next thing if it's a linked list, because I need to know what comes next. All right, so in order to create a linked list, we need to define the struct for the node. So you need to tell me what is in your node. You need to have a pointer to keep track of where the start of the list is. So I need to know where that head of the list is. And also if you are interested, sometimes the end of the list is called a tail. Computing people are always super creative with names. So we've got the head and the tail. And then we also want a way to create that node and connect it into our list. So I'll go through it in images first, and then we will do some code for it. Okay, so let's say we want to create a linked list with numbers 1, 2, and 4. Okay, so before what I did is just I made the list for you, and that's that, and just kind of linked it all up. But I want to know, how would I create that list? And the way I would create it is by creating a pointer at a time. Not a pointer, I'm sorry, a node at a time. But each of those nodes does have a pointer in it. So first of all, I want to have a pointer that knows where I start my list. And that means that it will point to the first node of the list. So when I create that pointer, I'm also creating the first node, okay? Because otherwise, what's my head pointing to if I don't have a node there? So by default, that means I'm also creating the first node. And my node that I've created is really, this shouldn't say 0, this should say null. Sorry. This should say null because when I create my pointer, it's pointing to nothing, it's pointing to null. Okay, so let's say I've got my pointer now, my head, I'm pointing it to the head. I've got I've done my 1, so my 1 had the null pointer and the data 1. And then I'm going to insert at the head. I'm not really digging this diagram. It made a lot of sense when I was doing it, but I'm not digging it right now. Let me draw it instead. Okay. And you know what? Maybe I'm going to use the nice boxes that I created here for myself. I did not mean to do that. Okay, I'm going to make a little bit of space here. Okay, so make a linked list with the data 1, 2, and 4. Okay, so let's say we start from, where should we start? So maybe I'll start with my 4, because then I'll keep inserting at the head, okay? So let's say I want to make a node with my int 4. What will happen in that case is that I'll create this struct node. and I'm going to give it data is going to be 4. And because I've created it, I don't know if there's anything else in the list. I'm not going to point it to anything. I'm just going to have null here. But when I've created it, I've also got a head that will point me to this node so that I know where it starts. And let's give this node an address. Again, very random number. So in this head, what is being stored, this pointer, is this address that will let me start my list. Okay, great. Now I want to make a node with the number 2 in it, and I want to insert it at the head. So I want to insert it over here. So I want to push my 4 over, really, because I want to insert it here before the 4. Okay, so what am I going to do? First of all, I'm going to create a node. Okay, so my node is going to have the number 2. And because I've just created it, it's going to be pointing to nothing. So I'm just going to point it to null. And now what I want to do is actually, I want to point this pointer here. I want to point it to my 4 because from my list, I go from the 2 to the 4. So in that case, I'm going to point it to the memory address of my node that has the 4 in it. So 0xFF0. So what that means is this address now goes to here. This one is still going to null. So this one is still going to nowhere. But now my head is still sitting pointing to my 4, whereas I want to shift my head to now point to this node that I've created, the 2 here. So if the address of this one, for example, is that I'm now going to change my head to point to the new place. So to point to the 2. So what that means now is I've got now my 2, and my 2 is pointing to my 4. And my 4 is still pointing to the null. So it's going nowhere. But the head is now sitting and pointing to my 2, which is at this address here. So inside here, I'm going to have, and this is my pointer head. Okay, so now let's say I want to insert that 1 in there. So now I want to insert the 1. So I'll create a node for a 1. And I might create this node, and then I'm saying, okay, I want to insert it at the head. So I want to insert it somewhere in here, which means that my head now has to point to this node here. So what I'll do is I'm going to change my head to point to this node that I've just created. Now that means that this arrow is gone, and I'm actually going to this one from here. But this is still pointing to null. So now I need to point it to what was currently at the head before I started changing things. So I'm going to point it to the address of this one. So I'm going to get rid of null, and I'm going to make it instead point to the number 2. So now it's going to go to this one. And this is still doesn't really need to be touched. It can just remain as it is. And that's kind of a basic, slightly messy way to create this diagram. I really need more screen space, I think. I will draw it nicer again. Let's see it in code as well, and then I'll have the diagram next to the code, and then we can go through it as we move along. Okay, so the first thing we're doing is we're defining a node. No, Becky, great question. You will not have to type out the memory address. Remember, we have a way to access memory addresses. Yeah. So we've got a node. Inside the node is my data, and inside there is also the pointer to the next item. So the first thing I'm going to do is I'm going to do this create node business. Okay. When I create a node, okay, we need to think about what would be the input to this and what would be the output. So when I was creating each of these nodes, what do you think I need to create that node? What do you think I need 2 things, and I was putting 2 things in here, and what were they? either my diagram was terrible or there's a little lag. I hope it's a little lag. Yeah, a data and a pointer. Yes, 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 yes. Well done. So I was creating each one with an int data, and also I was giving it a pointer to the next node. So I'm going to have a pointer to this struct node because that's what I was pointing to. So struct node, and you know what? I'm going to call it next, just to, you know, really throw it out there. So it's going to the next node. Okay, excellent. And what do you think? Okay, this is a slightly harder question. What do you think would be the output of that create node function? What would I be returning from it after I've created the node? What do you think I want to send back? What was the item that allows me to access the linked list and that I was changing each time I was inserting at the head of the list? What do you think I need? I do need a pointer. Excellent. A pointer to what though? What do I need to know to be able to access my list? It is an address, yes. What is it an address of? What do I need to, where would it be an address of this one? Or would it be an address of this one? Or would it be an address of this one? Oh, that's a lot more than I bargained for. What would it be the address of? What am I returning? Okay, so Lisa, you think pointed to new node? Maybe. I mean, yes, it is. It is in this case because pointed to the new node, I'm inserting it at the head. So I really want to know where my head is. Yeah, so someone's address of the head. Well done. So, and it is, it's a pointer to the new node in this particular case because I've inserted it at the head of the list. So I want that pointer to the new node. So I will be returning a pointer to that node, which means that I'm returning again a struct node. Oh God, a struct node pointer. And it's going to be the head of the list. Okay, we won't touch the print list yet. I might just comment it out for a second. Okay, so if we were to create the list, we can see that what we're doing is we are giving, we need to create the list by giving it a piece of data and also a pointer to the next thing. So if in my main I start creating things, I'm going to create this head. So I'm going to make a pointer and I'm going to call it the head because this is going to be pointing to the first node of the list. So if I've made this head and I want it to point to the first node, okay, this is where I'm going to create my node. So I'm going to use this function create node, and we've seen that what is going to go to that function is the data and a pointer to next. Now, when I've created this node, I want to give it the number 4, and I'm going to give it a little null to go with it because it's not going to be pointing to anywhere. I've got nowhere for it to point still. So that's going to create the head, and it's also going to create a node 4, and it's going to return for me, and it's going to give me that address back. Okay, so then if I want to create the next node, that should say 1. Okay, if I want to create the next node, and remember again, I want to change my head, so I'm going to return a struct node from this create node. And we've said that what that struct node that I'm returning is that it's going to be a pointer to the first node. So it's going to be the head. So my new head is going to be whatever node I create in here. And I'm going to create a node with 2. And where will I point that to? So if I've just put in a 2, then it's going to go to the head. So what that means is you're making a new node, the head of the list, okay? And then if I create my last number, again, my new head is going to be a created node with 2 and head. Okay, and I'm just gonna pop that off for a second, just so you can see it compiling. Okay, so now we've got this one. So I'm just gonna copy the definition down so that I don't make a mistake in the order. Okay, yeah, well done, well done. Okay, so now let's have a look. So what do we do to create our head? Okay, So you've seen what I was doing. I need to create that node first, okay? So the first thing I'm doing over here is I'm going to go back down to a blank space. Let me find a nice blank space for me here. Okay, so I want to create that node. The first thing I'm doing is I'm making up, where am I? Okay, so the first thing is I'm creating, it's not, now it doesn't want to draw where I am. Okay, I'm going to just draw from here. Nope. It's just not letting me play at all. Okay, let's do it like this. Okay, I've created a node. Okay, what do I need to do if I'm creating a node? How will I create this node? I need to give it some space, right? Because that's the whole point of using a linked list, is that I've got, it's a dynamic growth. I can grow it as I need it. So the first thing I do when I create a node is I malloc some space for it. So if I'm going to malloc some space for it, okay, and we did the malloc just yesterday, so let's have a think about how we would do it. So I'm going to create a new node, okay, so I'm going to have a struct node, let me call it new node, okay, and I'm going to create that new node by giving it some space, okay, so this will give me a pointer to that new node, okay? So I'm going to malloc, and then I'm going to use size off, and it will be size off that struct node, because my node has to have in it whatever is inside that struct. So it has to have space for that data and also the variable address to the next struct node. So what I've done is put too many brackets in there. Okay. So the first thing we have to do is we need to create a pointer to a node of type struct node, okay? I've called my pointer new node, okay? Because that's what will have the address of my node, and I've given it some, sorry, that's going to store my, the chunk of data that I've just created. Then I use malloc to create that chunk of data. So remember, inside here for malloc, we give it the number of bytes, and we return a pointer to the chunk of memory that was made by malloc. So my chunk of memory is stored in this new node here, and I've given it the number of bytes that are equivalent to creating a node. Okay, now I want to initialize that node. So I've got my new node, and my new node is a pointer. It's a pointer to this address, to the memory address of this node that I've created. So I can use this arrow to access whichever member of the struct that I want. And so I want to put the data, so into my data. So what that means is I've gone in here and I've decided that inside here into the data, I'm going to place my number. So whatever that number is and whatever number that I've passed it in my int data. So that means it's going to be equal to data. And now I want to initialize the next. So I want to initialize where my pointer is going to go. I'm sorry, I don't know why my drawing is now completely off kilter. This is what happens when you use Microsoft products. Ah. Okay, and then I'm going to have my pointer here as well, okay, when I create that node. So I've got the pointer here, and right now, because it's a node that I've created, there's not much happening. You know, where am I going to point it to? What do you think? Oh, someone, yes, it's very true. Yeah. Don't ask me for my feelings on Teams then. Okay, so what do you reckon? Because here, when we create our node, we're giving it the data and we're also giving it what to point to next. So we've actually given it the place where we want it to point, which means that I'm going to set my new node pointer. So my new node next is going to point to next that I've given it. Okay, so I've given it this next here is this address here, and this is what my new node is. So what I've done is I've initialized this here to be whatever data was given when I've created it, and I've initialized this to be whatever the next point is that I've given it, okay? So, and what will I need to return now, do you think? I mean, you've said it, yeah? We're returning the struct node. We want to return the new node because the new node is where we have stored the address to the head, okay? So that's where we've stored that first bit that's going to point to it. It's the address of this node here, and we're inserting at the head. Okay, so what that means now is potentially we have this lovely node that's just going off and happening, and we will not get a chance to see if it's happening because we need to be able to go through the list and perhaps read through it. So what I'll do, we've just created one node for now, okay? And that node, oh no, we've tried to create 3 nodes here. Oh, and I've also made a mistake here that I've now realized someone pointed out. Okay, so let's see what we've done here. Okay, so we've got this create node for null. Okay, so what does that do in the code? We've called this create node function with for and null. So what happens here is, let's say the first time we go through it, we have said create, and we're giving it for and null. So then what that means is when we go and we malloc some space to the new node is now a pointer to some address that points to that node, okay? Okay, great. So now we want to place these things into the node. So over here, we've initialized the first part, and what that means is we've said, okay, we want new node.
Decorated war vet, unite the colonies through more debt, fight the other founding fathers till he has to fall.
To be equal to 4. And what we want then is for it to also point next to null. So the next thing over is going to point to null. So we have said, okay, now we want this new node and we want the next thing in the new node. So my struct node next, pointer next. So that part of the struct, that's now going to be pointing to null. Oh, we should play something during the break, I think. Thinking music. Thomas, you can line something up fun. We've got another few minutes till the break. So let's, commercial break. That's a great way to put it. Let's do that. I like it. Okay, and then we're returning that address of the new node. Okay, fantastic. So then we have the new next thing. We want to create a node with 2 and we want to point it to the head. Okay, so now after this, I'm sending it to and the head. Now remember that the head is currently, I've created it here, and currently the head is pointing to this node that has a 4 in it, okay? So the head is currently at 4, and I want to point it to the 2, basically. So then that means that my new node now that I've created is going to have the number 2 in it, and it's going to be pointing to the head. So that means that my new node and the pointer to the next one is now going to be to the head. And the head at this point was pointing to 4 before that, okay? Oh my God, someone just said I can sing for you. You do not want that. That will just ruin your life. give you nightmares. My mum used to say that an elephant stepped on my ear when I was born. Okay, and so what? And then we return the new head. So we return now the new place where we're pointing to now, which is that node with the 2 in it. Okay, so how about we take a little break now, and then we can see what happens when we print it out as well, and we can draw it up again, and I can fix why on earth my pen is drawing, 10 centimeters above where I actually mean for it to draw. So let's have a short break. Thomas maybe has lined up some music for us. We'll play a little song, and you know what? I'm going to do, wait for it. I'm going to do this thing here. All right. Welcome back. I am loving all of these suggestions, strategies, and ideas. I can see that quite a few of you have cats from the suggestions that you're giving. This problem appeared in The Guardian a few years ago, and it kind of led to people just trying to prove things over and over and over, and mathematicians got involved to solve this problem. Turns out cats are just quite stealthy. But if you are interested, there is a solution to it, and it's a really interesting solution. I've put up a video solution to the question. It also has a link to the Guardian article. The Guardian article had 7 cats. I've reduced, 7 boxes, not 7 cats, and I reduced it to, no, the Guardian article actually had doors and cats. I went with boxes just because why not trap them? Thomas actually came up with a really good strategy. Why wouldn't you just get a dog? And then, you get there and the dog will run with the box with the cat. So no problem. So lots of good strategies, but yeah, there's a solution, a mathematical solution for you if you feel like having a look and if you're interested. Lisa asked if we actually covered free yesterday. We did indeed cover free, and we will do more freeing next week as well, because we will be, we're going to, so deleting nodes is probably the harder thing to do in a linked list, and we're going to do that next week after we've had a bit of practice moving around linked lists, and then we're going to practice freeing that memory that we've created for each node. All right, so I've managed to fix my Microsoft. This is called me fixing it. I guess you didn't see this situation. This is just anger at it not working. So let's. I have managed to fix it. So let me try and draw on it. Of course, it's not going to work now that I'm ready to get ready. Okay, I wanted to run through the code with drawing it to show you the benefits of drawing this lovely thing. Okay, so the first thing we're giving our create node function is we're giving it a for and a null. So here I am. Okay, so the first I'm giving is a for and a null. And I'm sending it to create node. Okay, so the first thing that happens is that I take that data, and then William, can you delete a node by linking the JSON nodes and freeing the node to delete? That is exactly what you do, William. It's just that it can get hard with where you delete and what you point to, and not trying to delete a null kind of thing. So we will look at it next week. But that is absolutely the theory. That's the beauty of linked lists, is that you move around your pointers, and then you can free memory if you need to get rid of something. Okay, so first of all, we malloc some space, and we create, when we create this, we give it the number of bytes of the struct node. I'm just gonna, so that you can actually see the code, I'm gonna go here. Okay, so I'm on line 49, struct node, new node, malloc, size of struct node. Who said that C is a wonderful language to understand? Obviously that all makes sense. But what you're doing there is you are creating a node. I'm creating the space for a node. And it's enough space to hold all the struct components. And my struct components have 2 things in them. So what I've done is I've basically, in this line, I've created this node by using malloc, and I've created a pointer to this node, which is my struct node new node. So my pointer returns to me this here, okay? So the head is not, the head is where we are pointing. The head, okay, Caitlin, excellent question. Is the head the first node or the pointer to the first node? And the head is the pointer to the first node, but that pointer, so it's not, the pointer inside it has the address of the first node. So your head is where you are starting your list, okay? Okay, so that's what that line 49 did. Okay, so now we move here and we say new node data is equal to data. Okay, I've sent it a for, and I'm putting that 4 inside here. That's what I did on line 54. I then move down to line 59, and I say new node next is equal to next. Now, what did I send? I send it a null, which means that I'm placing that null in here now. So what that means is that this is now going to nowhere. I've created this node first of all. Okay, excellent. The next command I give it is I'm saying to it 2 and ahead. Okay, so I'm giving it the number 2 and I'm also giving it head. So again, I've gone up here and I've said struct node, new node, malloc, size of struct node. So I'm creating this node here. So I've malloc some space for it, which means that I've created my bare bones of this struct and I've got enough memory to hold on to it. Okay, and let me give this an address for it so that you can see. Again, random addresses. So in this new node is actually 0xFF2 right now. So I've created this new node and I've returned the address to it. And I've got my new node here. You can't see what I'm drawing because I haven't moved my screen. Okay, so I've got this new node here that I'm returning to it, and inside this new node is the address, so the pointer to this node. So I've malloc some space for it, but there's nothing going on, okay? Oh my God, what on earth is going on? How did it move that? I did not even do that. I've got a ghost. Could say it's one of the dogs, but they're just asleep. Okay, so then we move on to line 54, new, zoom in, yep. Okay, that's probably too much zoom. Here we go. How's that? Is that better? Okay, so now we move to line 54 and we say new node data is equal to data. So that means that we've sent it a 2. So the 2 is going to go in here. And then we move on here and we say new node next is equal to next. The next we gave it in this case, okay, is the head. We gave it the head as the next item. So what happens here is I'm actually saying, okay, this is going to be what I gave it. And the head right now is sitting, this is my head, isn't it? So if this is my head, I now want to point it to this node here, which is sitting at 0xFF2. Okay, and what I'm saying now is that when I return my new node here on line 62, I'm returning the address to the new head, because in my main, I've said that my head is now equal to whatever this returns to me, okay? So it's now returned to me my new node. So now this is no longer this. I'm now pointing to here, and my new node is now the head of the game. Okay, so this is now the head. You can insert from the back of a linked list. You can insert in the middle of a linked list, but today we're only doing at the head of a linked list. You can insert wherever you want, okay? So you can really do whatever you want with this linked list. It's got a lot of flexibility. As long as you know where the head is, you can do whatever you like, okay? So right now we're just going to do just one, just doing it from the head. And then on Tuesday next week, we're going to do inserting in the middle, inserting at the end, and inserting everywhere else. I'm not sure what the questions are. What if Sarah can clarify what she means? That would be great. And I'm using an iPad. Okay, and then we have our last one that I've sent to it. I've said to it, okay, can you please create a node? And I'm going to give you data is 1, and the head is going to be my next. Okay, so I'm going to have to zoom out because I've drawn so big. No, I'm just going to go here. Okay, so I'm going to create another node on line 49 when I'm calling for malloc. That means I'm creating space for this node of struct node type. Okay, and let's say this has the address 0xAA5. And that means that my new node is now going to store the address that I've just, for the memory that I've just created. So it's going to be a pointer. And now I'm ready to initialize that pointer. Okay, so my new node data is equal to the data that I sent it, which in my case is 1. And my next that I've sent it, so I've sent it struct node next is the head, okay? So I want to point it to the head. Now, before that, I returned that this is here, this here is the head, okay, at this address, which means that I'm setting this address at 0x. I don't know why it stopped working. BB3. Okay. So I've sent it now. This is my new head and I'm returning, which means that this is now pointing here. So, and I'm returning this as the new head. So now this is my head over here. So what it means is my list is now head is pointing to the first node. Then I move on to my other node and then I finish with my last node. Okay. So the head is modified in this case because I'm inserting at the head. So each time I insert, I need to let it know that actually I've got a new head of the list now. My list starts somewhere else. Because I'm inserting at the head of the list, what it means is that I've got a new head. Okay, so let's have a look at what else we have. Let's see. Okay, so now we've got all of our elements in here. We've created 3 nodes. Okay, we've created 3 nodes, and now we want to actually now we want to print it out, I guess, so we can see what's going on. So let's have a look how we print out. So if we print out from a list, we need to be able to go through that linked list, and each node that we get to, we're going to print out. Okay, so let's have a look. So I'm going to go back to this helper function. So what do you think our print list will need as an input to be able to print out the whole list? What do you reckon you need to give your linked list print function? How would you go through that linked list? What do you mean? Becky, you've asked, do we only have to malloc once? You will malloc every time that you create a new node. Yeah, well done, Lisa. Absolutely. So we're going to give it the head because the head is what allows us to go through the linked list. Okay. So that's where we want to be able, that's where we start. And that means that we can then follow all the different addresses. So a linked list is basically like a scavenger hunt. You've got to go to one place to get the address to another, and then you've got to go to the next one to get the address to the other, and so on and so forth. So when I'm sitting at the first node, the only way I know that there is a next node is that there's something in that next pointer telling me. But I don't know how many things there are in that linked list until I make my way through that linked list, because the only information I have is the information on the next node, okay? So Lisa was right. We are indeed giving it the head. So I'm going to give it a struct node head. And what do you think will be the output of a print list function? So what do we reckon will be the output of the print list? Yeah, void. Well done. Because I don't really need to return anything. I haven't changed anything when I've done a print list function. All I'm doing is printing stuff out. Okay, I don't need to return anything back to the main function. I can print it inside my function. Okay, so let's have a look and see how we can implement this function here, how we can traverse the linked list structure. Okay, so let's have a look. Okay, so when we have this linked list, and I'm just going to go down again, and then I'm going to draw this linked list for us. Okay, so we've created a linked list that looks something, Microsoft Word whiteboard just carked it. We've created a linked list that looks something like this. Okay, here I am. Ah. Okay. Can anyone see that, or is that not clear? It hates me. It just hates me. Okay, so we're going from this node here. This has a pointer to my next node. This has a pointer to my next node. So this is what our list looks like now. And then this is going to null. Okay, and then here we have the head that's telling me where I start. Okay, so when I'm traversing through the linked list, okay, you are right that I give it a head as my input, okay? So what happens when I've got that head? I'm ready to start. And what I said to you before, when I've got the head of the list, I need to be able to move through it one by one node. And then that's what gives me, you know, the actual data that is stored inside those nodes, okay? So let's say I want to, the first thing I want to do so that I'm not changing anything, okay, is that I want to be able to oh gosh, okay, I didn't mean to do that. I was doing, okay. So create a way to keep a track of where we are in the list, okay? So one of the most common things that we do when we traverse the linked list is that we say, okay, I'm not going to change things by changing the head of the list, but what I'm going to do is I'm going to create a pointer called current, which allows me to keep track of where I am currently in my list, okay? And the first thing I want to do is I want to set that current to the first node, obviously, because I want to be traversing the linked list. So what that means is I'm going to have a struct node pointer called current, and I'm going to set it to the head of the list because that allows me to know where I am on the list right now, okay? So now I want to be able to loop through. If I'm looping through a linked list, okay, how do I know I've gotten to the end of the list? What signals to me I am at the end of a linked list? Yeah, so it's when we reach null. Yeah, null, well done. So when we get to null, we know that we're at the end of the list, okay? So what that means is that our while loop condition is going to be whilst that current is not equal to pointer, while that current is not equal to null, we're going to keep moving through that list. So whilst this current is not over here equaling null, so while it hasn't moved to over here, we're going to do something inside this while list. So what happens then? Okay, we're going to print out the value. So I need to give it some value. So what I want to print out is what is inside the current, what data is stored in there. Because remember, the current right now is just the head of the list. I've just made basically a copy of the head and I'm accessing using this current pointer. So my current and my head at the first instance are pointing to the same thing, okay? And then my current will move along, my head will still stay pointing to that first thing. Okay, so my current is now sitting here and I've accessed it for the first data point, which is 1. So I've printed this 1 here, and then I want to increment it to go to the next node. So that means I want to change my current to be on this node over here, on the second node that has the 2, okay? So if I access this next pointer here, if I go to current next, what it will do is it will move this current to over here. So every time I go current next, I'm moving across to my next node. So now my current is over at the next node. So to increment, we do current is equal to current arrow next. So you're accessing the address of the next node and then you're pointing to it. So you've moved along the list by 1. So what we then have is we've now been able to loop through the list. I finished it off with an X just to make it look good. And then that will be the first. So then I move it along. I'm going to print out the new, I'm going to check, is this current equal to null? No, it's not, because it's sitting over here. So it's not equal to null yet. So I'm going to print out number 2. So I've got it 1 now, and then I'm going to print out 2. And then I'm going to say, okay, that means I'm going to move my current onwards to this one here. So my current is now pointing to the third node. Is that equal to null? No, it's not. So I'm going to print out the value in this node, and then I'm going to move it along to the next thing. Okay, so now my current is pointing at null. My current is actually equal to null now. And what that means is on that next loop of the while, it's going to say, is current equal to null? It is. So I'm not going to go inside the while loop again. So I'm going to come out here and I'm going to print the X to finish up. Yes, it should be. Good style pickup. Well done. Okay, so let's have a look what it does. Okay. Okay, and let's run it. And nothing has happened. And why has nothing happened? Who knows why nothing has happened? I think it's because we didn't do anything. We didn't call the print list function here. So it's not really printing anything because we haven't told it to print anything. So when I print it out, what I want to give it is I want to give it the head. And remember that the head inside it just really has the pointer to this node, okay? So it's really just giving me the address of the first node. It's letting me know where to start. So yeah, that's right. We did not call the print function. Okay, let's try this again, this time calling the print function. And I'll run it again. And so now it's printing out the list for me. So 1, 2, 4, and then I finish it off with the X, okay? And remember, we're inserting at the head. So 4 became my last node, and then I inserted 2, which means that 2 goes before it, and I insert 1, which means 1 goes before it. Okay, so then we have 1, 2, and 4 as our list of items now. Okay, so that's good. So we've got 2 ways. We've got a way to traverse the linked list. We've got a way to add nodes at the head. How about I throw a spanner in the works and I break this up into a multi-file project just to give you a little bit of a revision of how we did that yesterday as well. Okay, so if you remember, to make a multi-file project, I need 3 things. I need my header file, so my .h file. I need my implementation file, which is .c file, and I need a main.c file as well. It's going to be a problem because it's going to bring me a different main file now because I made another main file. I've just realized that there's another main file in week 7. So what I'm going to do is I'm actually going to make a new directory for it. I'm going to share it with all of you, so don't worry about this next command. Okay, and now I'm going to make a header file. I'm going to make an implementation file, and I'm going to have my main file. Okay, so who remembers how we're going to break things up? What happens in my header file? So the .h file, that's my header file. Okay, so we include any function prototypes here. Yeah, and any hash defines and any comments. That's right, well done. So any hash defines and any comments. So we've got 2 functions in our linked list so far, and we will keep building on it. We've got these 2 helper functions here. So I'm going to copy them across. Now, yesterday, someone asked something, a very good question. Where do my structs go? Do they go in the header file or do they go in the implementation file? I can't remember who it was. I think it was Neil, actually. Anyway, so basically, there are 2 schools of thought, of course, as with everything. If you put them in the .h file, when you include the .h file, they're available everywhere, okay? But the problem that this has potentially is that you're locking it into one particular struct that you're forcing everyone to use. So I subscribe to the school of thought that the struct goes in the implementation file, because that means that it's then available to the particular implementation that I've designed. And the reason for that is usually the header file is the one that's shared amongst different programmers. The header file is the one that you look at to know what functions you need to write. But the implementation file is where you actually solve the problem, okay? And if I'm solving the problem there, then I'm going to have a certain type of struct there that will solve my problem for me, okay? So in that case, I will put my struct in the implementation file. You might see different things. If you want to force, your whole team at a certain point to use a particular struct or a particular structure with particular things in it, then you might put it in the header file, because then you're forcing them to use a particular implementation and way to think about it. Okay, so we've got 2 prototypes in here, and then now we'll move to our linked list.c file. So if you remember, what do we include in here? So what should we include in here? So I suppose I'm going to be writing some code and I'm going to be maybe printing stuff out. So I'm going to include my normal standard library. But what else do I need to include? Yeah, so functions, but my prototypes are in the header file. Yeah. So then I want to include my header file in here as well. And remember, if I'm including my own header file, it's going to go in double apostrophes. So I'm going to tell it to include this linked list.h, which is going to tell it to include my header file. Okay, then that means I'm ready to implement my 2 functions, which were here. So my create node and my print list function. So I'll copy those across into my implementation file. Okay, so now the implementation file has my create node and also my print list function. And finally, the main.c is going to have my main function in it, the one that actually makes all the calls out. So I'll copy that across, and then we can see what do I need to include in my main function. So I would imagine that I need to include, don't need to include that. So what do we need to include? What else? Okay, so we need to include our header file. And then are we using anything else in here that might need Okay, so in my main, I include my linked list, .h, so my header file to let my main function know what's going on, yep. And then I also include my standard input output, but I don't really have anything that I've used the input output for, but just force of habit, I suppose. Now, I think I'm missing something because in this function here, in my create node function, I call malloc, and malloc is included not in this standard library. So I need to be able to include the library also that has malloc in it, which is the standard library.h. So it's just a C standard library, but I need to include it in there. Okay, so let's have a look. Let's save all of these, save, and let's see if we can compile them. Okay, so DCC, remember when we're compiling a multi-file project, we compile all the C files, not the H files, because the H file is included in the C files. And I'm going to call it LL. And I've got madness. Got so much madness. It's just screaming at me. Let's have a look. Why is it screaming at me? Size of struct. So I've made a mistake somewhere. And that mistake is not defining my struct. Yeah, that's exactly right. I have not defined my struct, which is why it doesn't know what on earth I'm talking about. Okay. So the struct, there's two ways to go about it, which is what I kind of was saying before. It can go in the .h files, but it means that you're forcing everyone to use the same implementation. So usually we would just put the struct in the implementation file, because what that means is that you are actually implementing it how you see fit, which is, you know, similar to how it would be. But there's two schools of thoughts as well. So if you want to force people to use the same struct across the whole like team, then you would put it in the header file, because then everyone is forced into a certain implementation. Okay, and then if we run it, it's going to do everything again the same way as before, but this time it's broken up into, you know, a multi-file project as opposed to, a much smaller one big program. And the reason I did that is because you will be using multi-files in your assignment too. So I wanted to do the multi-files a little bit more just to see what's going on. All right. Let's have a look. Okay, what's next? Okay, any questions whilst there's still simple implementations of it? Because I'm about to put it into a different context, this linked list situation, but I want to make sure that it makes sense with a simple list of numbers before we go on. Yeah, we're going to be going over linked lists for the next 2 weeks. I don't expect you to understand everything straight away. I really wanted to go kind of slowly today, only 2 things we've done, how to insert, how to go through it, because I think it needs to sink in a little bit. And then we're going to go through it again, but we will be going through it. All of next week is just linked lists, and we're going to be playing around and manipulating them in different ways. And if you've never seen linked lists before, this is quite hard, and this is going to be a little bit of just a mind blown, because it's really different to how you've done things before. It's really different to arrays. Okay, so you will find it difficult to start with until you can apply it and practice it yourself as well. And again, please try and draw it out every time you do a problem, because it kind of really simplifies it. And I mean, I subscribe to that for any problem at all. You should diagram out a problem before you start writing code, because it makes it a lot easier. You can't access the files. You can't access the multi-files. Okay, it's because I think, oh yes, you can't access, yes, because they are all, yep, sorry, let me make them available for you. There we go, they should be available now. All right, I think let's stop having the conversation about dropping out of the course, because I think this is a difficult course, and that's, you know, I think it's really important to acknowledge that, because it's combining a whole bunch of things, and, you know, a lot of these concepts are also very new to you as well. So please take your time to understand them. Please ask lots of questions, okay, as well, because these are not easy concepts to understand, and these concepts make a really big difference as you move through your degree as well. This is an introductory course, which means that we want you to get a very good basic grounding in what a data structure is, okay? Yeah, so I think, yeah, once you understand, you know, I think linked lists make pointers more obvious, and it kind of goes in that circular fashion as well. So, yeah, okay, and I think Neil up above said, how can we revise linked lists? You will have, you know, plenty of opportunities to revise linked lists. There's going to be a lot of labs surrounding linked lists. There's going to be practice questions surrounding linked lists. There's going to be a whole bunch of things that are all about linked lists, okay? We're really going to, because you need it for later points in the course, you need to understand what this data structure is, okay? And I really want you to understand it first before you, you know, before you go on to do it in different languages as well, because linked lists is not just a C thing, it's a data structure that we use in computing. Okay. Okay, let's shift the focus away from that, and yeah, you know what? Linked lists are actually quite cool. I think the first time that you see them, they're confronting, but as you start using them, your head will be held together very much when you're using them. Okay, let's have a look at a slightly harder problem. And we have also actually made a linked list video for you as well. So we will point you to more short linked list videos too. And you, just as with everything else, you kind of need to practice them as well. And also let me know if something is really not clear, because sometimes I get a mental block, and because it's clear to me, I don't go down into the nitty-gritty enough. Okay, let's have a look at our problem. and we can just start it today. We're basically just going to create another linked list, but with a slightly different things in the node, because I want to show you that a node can have something more than just data and int, and that's it. What are some common uses for linked lists? Okay, there's a lot of uses for linked lists, and basically the okay, usually when you have a structure where you don't know where things are going to be needed, so you do not know how many things you need, that was a really good example from yesterday, okay? You have a linked list to create the structure because you can dynamically allocate memory. An application of it is also because you access linked lists sequentially, okay, you can store the data from a linked list across the heap anywhere, right? It's all scattered through. So what it means is that it allows you to be a little bit more efficient in memory. Sometimes a problem is going to be, perfect for an array, because what it does is that it, we need to be accessing things, continuously. We don't care about wasting 1,000 spaces, but a linked list doesn't waste space because you create nodes as you need them and you insert them as you need them wherever they are. So think about it also when you have an array, okay? If I have something at array index 1 and at array index 3 or index 2, I can't insert something in between those two numbers. I can't shift them along because I've made a certain size of an array and I can't just add to that array after it's done, okay? Whereas a linked list, I can add things in as I want, and I can put them in wherever I want. So an array has this limitation in that once I created my array, at compile time, I said the size is 100. That's it. I can't make it any bigger. I'm done, okay? So if I want to add something to the back of it, if I want to add something to the middle of it, I can't, because I can't do that. And if I'm adding to the middle of an array, then shifting everything down by 1 is going to be a big job, okay? If I'm adding between elements 2 and 3, okay? But if I have a linked list, I can easily insert things anywhere because all I'm doing is changing the pointers. I'm not changing anything off that list. I'm just literally inserting it in a section. And what that also means is I don't need to think about how much space I might need in the very beginning, okay? What it really is, I can create as I need space. I need a node, let me malloc some space. And then I can put it in wherever I want it. So in that sense, you would use linked lists for problems that require you or might require you to add in more elements and you don't know how many elements it will be, or to insert things in and you don't know where that insertion might take place, because it's a lot easier to insert with a linked list than it is with an array, because an array is limited once you create the size of it. I hope that clarified it a little bit. Okay. Okay, I'm now getting to the point where it's too late to start a new problem. Might be a good time to finish anyway. But, okay, I'm ready for more questions. Let's do 5 minutes of questions. Rapid fire. No one's got a question. And so also next week is all about linked lists, okay? We're not just skirting over it. We're going to give you time to really understand what on earth a linked list is. And I promise you, by week 9, you're going to be just like traversing that linked list, current, next, current, next. And then your mind will be blown when you can do next. Why don't we include the implementation file in main file? Okay, good question. The reason for that is because usually at an industry, you will have a team of people writing code, okay? And that team of people have their headers of what they're actually doing, and each one might implement things differently. The main file should not care how you're implementing things in the .c file. From the main file, you should just be able to call the functions as you need them, and you shouldn't care how that code is actually written. So that's why the implementation is not in the main, because they're removed from each other. It's like you're hiding the implementation from the main. So someone else can write the main, and then they shouldn't care how you implemented things. They should just be able to call the functions that they can see are available to them in the header file. Is there a way to tell the length of an array? There is a way to tell the length of an array. Yeah, absolutely. And you can do it by using the size of, actually. So what you can do is you can, because when you declare an array, you have to give it a length as well. And one way that you can do it, the length of it, is you can say, okay, and I don't want to blow your minds, but you can basically say the maximum number of elements divided by whatever the size of one thing is, and then that will give you the number of things in that array. Are binary trees just linked lists where each node points to two other nodes? Oh, that's a lovely question. That's a very good question. Oh, just balancing binary trees. You can implement, so each structure, binary trees are another structure in computing, okay? And it's a slightly different structure because there's parents and children and you can balance them. So, but you use similar concepts when you're implementing a linked list to that binary tree. And you won't do binary trees, I think, until next year. Yeah. What's a good way to tell whether a linked list is better for a task than an array and vice versa? Another excellent question. So in this course, in 1511, we do not expect you to be able to tell which one is the better data structure. We will tell you which data structure to use, okay, in any problem. So we will tell you whether to use a linked list or an array. But as you get practice using them, you will actually see what might be a better way to do things, okay? And I can implement one thing using arrays and the same thing using linked lists, okay? And when I use it, I can see actually the array version is not very efficient. The linked list version is better. And that really comes from practice and sometimes from doing it both ways to see which way is better and, you know, getting completely lost in the, and one example of that, we're going to be learning about stacks and queues in week 9. And I once tried in a lecture to implement a queue using arrays. And I think everyone and myself hated the day I started that lecture. We just wrote that lecture off because it was a big mistake to do it with arrays. It was so inefficient and so difficult. It just, even though you can solve it that way, the solution was pretty rubbish. Next one, and if you have pointers that are pointing to arrays, can you just keep adding onto them because you haven't had to specify their size? Okay, that's an interesting question. Like how big is a pointer? Well, a pointer points you to a chunk of memory, okay? So a pointer itself is a variable and the size of that pointer is going to be the size of what it's pointing to. So if it's pointing to an int, the size of that pointer is its of type int. If it's pointing to a struct, it's of that struct, and so on and so forth. So that's what a pointer is. Are binary trees for randomness? Binary trees are for searching and for sorting things. You'll learn all about it, balancing a binary tree. I was just reading through some linked list code online. In the code, they declare the head pointer outside of any functions. How does this course feel about that? I don't like to do that because you can get lost in where that head is actually pointing to. So you should point the head to wherever it is in your function that you're using. So again, we try and declare our variables as close to where we're using them as possible. And it's the same with the head. I want to have that head close to where I'm going to use it or in the function that I'm using it. Okay. More. If we use a lot of pointers with different names, do we need to use free to make sure we don't run out of memory? It depends. If you're using a lot of pointers with different, so if you're mallocing space for all of these pointers, so if you're making a lot of nodes, You don't want to use free unless you're actually deleting the node. Otherwise, you're getting rid of what's going on. So it depends what you are trying to do. And to be fair, it takes a while to be able to run out of memory on a modern computer. It's not so simple. I mean, I could do it if I set it on an infinite loop. Obviously, I will just keep mallocing and not freeing, and it will cause my computer to go, not today, thank you very much. But it's not that easy to do, okay? It's just good practice, and also you just need to free the memory, because otherwise you're not optimizing and making it efficient. Will we explore doubly linked lists? No, we won't. No, we won't. Not in this course. Then how much memory does the pointer itself add to the memory it's pointing to? So the pointer is just a variable. So it has its own number of bytes that it occupies, okay? And we say what it's pointing to. So is it pointing to an int? Is it pointing to a struct? And that's the space of that, it's got the memory address of the pointer that it's of the block of memory that it's pointing to. So the pointer itself doesn't add a lot to memory. It's just another variable. So you don't need to malloc a pointer, okay? I think I know what you're trying to say. So I'm not mallocing a pointer, okay? What I'm mallocing is when I make a new piece of thing, so when I make a new node, I will malloc some space for it. And malloc as a function returns a pointer to me that gives me the address of where it made this memory, because the memory is in a heap, it can be anywhere, okay? And that's why that's what it returns to me. All right, I think those were really good questions. Well done. Thank you all so much for tuning in. I hope the rest of this week goes well, and I hope that you're all able to finish the assignment really well and kind of feel good about what is going on. But we will reconvene next week for more linked list fun, and we will draw a lot more diagrams, and hopefully you have a good week ahead. So I'll see you all next week. Bye.
Cool.